Now, picking up from our previous discussion before the lawnmowers came and made it too loud for me to speak, we had a sample of size 70. I believe we were talking about cows, birth weights of cows or something like that. I'm just making these numbers up out of the blue just to have something to talk about. So I'm not making any claim about how accurate this is, as there's no way it can be accurate, but just to have something to discuss. And we had a standard deviation, as I recall, was 9.1. Now, this is our task. We want to know some information about where we think the population mean might fall. We don't know the population mean. That's what we want to find out something about. The information we do have is 70 measurements, which gave us a sample mean of 110 and a standard deviation of 9.1. Now, here's the thing. The population mean is on, the sample mean falls at, let's say, 110. Now, it could be, remember that we have working for us the central limit theorem, right? And we know the population mean, mu, falls in the middle here somewhere. And so when we take x bar, again, what we've essentially done is we've reached onto this x bar scale. This is the z scale, this is the x bar scale. When we take this sample mean of 110, essentially we're blindfolding ourselves, reaching down into this, and we just reach out and pull out one of the sample means, and we got 110. It could be that we got 110 from way up here. But that has low probability. It could be the sample mean is very much higher than the population mean. If I take this picture and translate it up here, that would correspond to the population mean falling way, way down here. Now that could happen, but you see that has low probability. What also could have occurred is when we reach blindfolded, when we take our 70 cattle, this is a random sample, so this is done totally blind, it's a random sample, we reach in and we pull out the sample mean. It could have been x bar 110 is way down here on the scale. That would correspond to the mean, population mean mu, being significantly larger than the x bar of 110. All right, that would correspond, maybe we could have overestimated, our value for mu could be here. We have underestimated the value for mu. It could be that the sample mean is either way too high or way too low of an estimate for the population mean. But again, that has low probability. The question is, what is high probability? High probability is that the actual x bar we found is in here, or maybe here, or maybe here, or maybe here. What has high probability is that x bar and mu are, roughly speaking, relatively close to each other. What has high probability is that the mu falls somewhere close to the x bar. We don't know, but we do know that there is high probability that this is occurring, and there's low probability of one of these two occurrences happening. What we want to do is put some specific numbers and some structure on that probability. Now, what we would like is something like this. We would like to be able to say, I'm going to pick a number out of the blue sky. Let's pick a number, say 10. Okay? If you add 10 to this, 10 units, that would put this at 120. If you subtracted 10, that would put this at 100. And now what we have, if you remember from your glory days in basic algebra, we have an interval of the number line. Do you remember interval of the number line? We have, here's 100, here's 120, and we have an interval of the number line. Remember doing this? This corresponds to the interval 100 to 120. Now, where did these numbers come from? I took 100, added the 10, and then I took 100, subtracted the 10. All right? Now, you can make this a little more concise we could combine these into one statement and say 100, and this is the key notion, plus or minus 10. 100 plus 10 gives us 100 plus 10, gives us 120, which is this top value. 100 minus 10 gives us 100 minus 10, which gives us the 100, gives us this bottom value. Where did the 10 come from? In this example, I just pulled it out of the blue sky. In our work, we're going to have a formula that computes this. But more on that in just a bit. First, just some terminology. Now, there's nothing magic about 110. I'm sorry, about 10 rather. What if instead of 10, about 3 minutes ago, if instead of 10 I had said the number 15, then we could take 110, add 15, and we could take 110 and subtract 15. If we added 15, I'll put this in red, if we use 15 as the margin of error, if we use 15 as this value, we could add 15, that would be up here at 125, add 15, and then we could also be down here at 95. Where did that come from? That came from 110 either plus 15 or minus 15. If you take 110 plus 15 or 110 minus 15, that would give you the interval from 95 to 125. So this expression corresponds to this interval. And this expression corresponds to this interval. Those are interchangeable. Now, some terminology. This is an interval of the number line, and we say it has a high probability of containing the population mean mu. It could be that the population mean mu falls somewhere in this green region, and that is the high probability region. Now look, the further out we go, the larger we've made this target. And so in the red region goes all the way from here all the way up to here. There is a higher probability that mu falls in the red region. And if I made one more, if I made a purple region, suppose instead of 15 we do plus or minus 20. That would go way down here to 90 and way up here to 130. And that would be an even larger interval. Or we could only do plus or minus 5. If we did plus or minus 5, that would only go up to 115 and down 105. And that would be a smaller interval. Now, it could be that mu falls in this small interval. That has a little bit low probability, because now what we're saying is, now we're making this target way too narrow. Now we're only considering this piece. So if you make this too small, then the probability gets small because you've reduced the width of this area up here. As this gets larger and larger and larger, there's more and more probability taken into account. So the blue becomes the green as we get larger and larger. This interval is larger than the blue, so there's a higher probability of that. And then the red is even larger than that. There's a higher probability. And the purple is the largest one we have up here. That has the highest probability. Each of these intervals has a probability value associated with it. Each of these intervals, we call them an interval. Here's the interval. This and this are interchangeable. This and this are interchangeable. Each of these is called a confidence interval. All right? A confidence interval. This is the terminology. X bar is called the point estimate. The point estimate is X bar. Point estimate. The point estimate. In this case, 100, oops, I've written this incorrectly. This is 110. 110 is the point estimate. And then the value that we're adding and subtracting. So, In this case, we added and subtracted 15. In this case, we added and subtracted 10. In the other cases, we added and subtracted 5. We added and subtracted 20. The value that you add and subtract, this value is called the margin of error. We have a point estimate, which is 110, point estimate plus or minus margin of error. So let me kind of clarify some of this. Get my eraser. Point estimate plus or minus point estimate plus or minus margin of error. Now what we're going to do is learn a process for computing these values, computing this interval, and then using that as an estimate for our value for the population mean mu. That's the beginning of the terminology work we're going to be talking about, and we will discuss the computations that give rise to this number and these numbers and what all this means. So there's part of the information we have, point estimate plus or minus margin of error, and more on this in a bit.